Consider a charge sitting here. I'm going to call this Q1, okay, and I'm going to put specifically an electron, which I'm going to represent just as a minus sign there. So that's my electron. And there's some distance r apart, okay. And so if I were to look at, ask what is the size of the force between them, well, I would write down over here. I'd write down force between them. It's Coulomb's force. It's going to be K Q1, and then E is the size of the charge of an electron, and it's negative since it's an electron, so I'm going to plug that minus sign right there. Okay, so that minus sign is technically from that E, and then divided by the distance between them squared. Okay. Well, what if I replace this with a proton? Okay, well, that would then be, in this case, so let me put a minus right here. Here would be plus. That would be a K, Q1, E. They have electron and proton have the same charge, just the proton's positive. So I have this E, but no minus sign anymore. Okay, over r squared. That's no different. Okay, well, what if, forget the proton or negative, what if it's just some other charge, some Q2? Okay, well, I don't know if it's attractive or repulsive now, but I'm just going to put F, I'm going to call it Q2, that's the force on Q2. Well, it would be K, Q1, Q2 over r squared. Okay. Now, in each of these three cases, this charge was the same, the distance is the same. All I did was I took this charge and I changed it. So, started with an electron. Okay, well, let's take that out, and let's put a proton there. Okay, we got something, we took that out, we put this random charge there. And wherever that changed, that was just whatever this second charge was. And that's interesting from a mathematical standpoint, and interesting even more so from a physics standpoint. The mathematical standpoint says, well, I can kind of reduce this and just say that there's something acting on this charge. And so if I group all of that together, which is the same thing as right there and right there. If I group that all together, just let's call it E, for example. I can call that's a negative EE. That's equal to a EE, and that's equal to a EQ2. Okay? That E is the same thing in all cases. Now, so mathematically, that's kind of made it simpler. I could just every time just find out how big this big E is, and then just multiply it by whatever charges, be it Q2, be it a proton, or be it a negative electron. Okay, now physics, the physics side of that is even more interesting. Is there something here? If I take a charge out and I have nothing there, it's just space. Is there something there that exists? And when I put a charge there, whatever was there before interacts with that charge? And this is the idea of fields. Now, it may seem kind of weird, but we experience it all the time. Gravitational fields. Gravity, I could replace this. This could be the Earth, and I could put a moon, or a satellite, or an astronaut, or a spaceship, and they'll feel an effect based on simply how big this mass is. And again, this would be an Earth's mass, and the distance between them, and then the size of the mass of that particular object. And so there are gravitational fields. Whether or not there's an astronaut sitting in this point in space, there is still a force, or there is a gravitational pull, or at least a gravitational field that's there that can then pull on an object that's placed there. So the same thing is true with charges. There is an electric field everywhere around this charge, and then all I need to do is place another charge there, and we call that a test charge. This would be the source charge, source of those fields, and then this is a test charge. This is what's going to happen when I test to see what happens to that charge. Okay, and so with that, this idea of this big E, we actually call this big E the electric field. So we can then reduce Coulomb's law to two parts. We can say F equals E times Q, and I'm going to put a subscript T, meaning the test charge. And I'm going to put this E sub S, meaning the source field, or the field of the source charge. And from that we can get that E sub s is equal to K Q, which I'll put an S there now to emphasize it's the source charge, over R squared. Okay? And we can even take it one step further, and we can assign the vector nature of this with the electric field. We know force is a vector, and we can actually put a vector sign over this electric field. So we know that if we put up, if QT it was a positive charge, okay, then and if ES, if R hat was pointing this way, it's pointing away from our source. Okay, if Q1 was positive and Q2 is positive, then the repulsive force would be in that direction. Okay, and what we'd say then is the electric field carries this R hat direction with the size of the source charge, and so ES points in the direction of this QS times the R hat. So if QS is positive, then ES points away from that charge. If QS is negative, then ES points towards that charge. So it'd be just either with the direction away from the charge or against the direction away from the charge. And so the electric field carries both the size of these three quantities as well as that direction, and we can then write Coulomb's law in this manner, which is really convenient because now I don't need to focus on what's going to happen to a specific charge. It's just what is this charge creating there, the field created there, and then we can add to that.